Hello everyone, and thank you for watching. Today we will present our work, LeAD-M3D. It focuses on real-time monocular 3D object detection and introduces a new way to overcome the inherently ambiguous challenge of inferring 3D depth from a single 2D image. First, let us introduce the task of monocular 3D object detection. The fundamental goal is to infer the 3D scene representation from just one RGB image. The input is simply a 2D image. From this, the model must solve the difficult problem of inferring the object's 3D location, orientation, and size. This task is extremely challenging because the 3D structure is lost when projected onto the 2D input view, and it must be recovered solely from 2D visual cues. This is particularly difficult for methods, like ours, that are free from geometric assumptions and trained without reliance on LiDAR-based supervision. Within the field of monocular 3D detection, our aim is to break the fundamental trade-off between accuracy and runtime. On this graph, we plot runtime on the horizontal axis against accuracy on the vertical axis. As you can see, most existing methods are constrained by a Pareto frontier. They are either fast but less accurate, or highly accurate but too slow for real-time applications. Our method, LeAD-M3D, completely surpasses this frontier. We deliver strong accuracy and true real-time speed simultaneously, setting a new Pareto optimal standard. As our first contribution, we propose asymmetric augmentation denoising distillation, or in short, A2D2. A2D2 is a LiDAR-free student-teacher-based training pipeline. At its core, it creates an information asymmetry between the student and teacher by making the student's task significantly harder than the teacher's. The teacher network processes clean images. From these, it predicts the 3D bounding boxes. In contrast, the student receives the challenging mix-up image. The student is then asked to predict objects visible in both source images. Next, we match the student and teacher predictions to their corresponding ground truth objects. We then distill the depth features from the teacher to the student model. To achieve this, we first extract the object-related depth features. Then, we distill the teacher's depth features to the student. The mix-up data augmentation is central to A2D2. Mix-up presents two source images to the model simultaneously. This is achieved by merging the images at the pixel level. The network then needs to predict objects visible in both source images. However, as we will see, this creates ambiguous ground truth-to-prediction assignments during the loss computation. You can see two separate yet overlapping car instances here. Our baseline matching criterion considers two factors. First, the predicted probability of the ground truth class. Second, the intersection over union between the ground truth and predicted 2D bounding box. Our baseline combines these two criteria to compute the final matching score. However, this approach creates ambiguous assignments in dense or mix-up augmented scenes like this. To address the assignment ambiguity in mixed scenes, we introduce our second contribution, 3D-aware consistent matching, or in short, CM3D. The core idea is simple. Incorporate 3D geometric information directly into the matching score. Here you see the two predicted 3D bounding boxes. We extend the matching score with the marginalized generalized IOU between the predicted and ground truth 3D bounding box. This metric measures the overlap in 3D space. In this example, the difference in depth allows for clear separation between the objects. This greatly reduces assignment ambiguity. Ultimately, it stabilizes both the standard training pipeline and A2D2. To further improve runtime efficiency, we introduce confidence-gated 3D inference, or in short, CGI 3D. Previous methods waste a significant amount of computation by running the expensive 2D and 3D prediction heads densely across the entire feature map. We aim to improve this by performing 2D and 3D inference only on high-confidence regions. The key idea is to leverage the score map produced by the class head, which indicates object confidence across the image. Based on this score map, we identify high-confidence object regions. We extract 3x3 feature patches corresponding to regions with the top Ka highest object likelihood and discard the rest. Only these selected patches are then passed to the 2D and 3D heads instead of the entire feature map. This selective processing avoids running expensive regression heads over background areas like sky or buildings. This results in a strong decrease in flops and significantly accelerates inference. Thanks to CGI 3D, we achieve a 3.6 times faster runtime than the current state-of-the-art model, MonoDiff. In the next set of slides, we present qualitative results from several datasets. These examples illustrate how our method behaves in real scenes and how accurately it captures object geometry under different viewing conditions. Our approach generalizes to diverse perspectives. Here we present qualitative results on the traffic view dataset, ROPE 3D. We compare our approach with the baseline YOLO 10-3D. In the bird's-eye view representation, you can observe that LeAD-M3D consistently achieves more accurate depth estimates. Thanks for watching. If you would like more information, please take a look at our paper and visit our project page.